C# and AI Masterclass by Edgar Milvis Volume 8, Chapter 7. Let's discuss Chapter 7, Converting Existing APIs into Plugins. Now, let's explore theoretical foundations. The theoretical foundation of converting existing APIs into plugins rests on a fundamental paradigm shift, transforming rigid, procedural HTTP endpoints into dynamic, semantic capabilities that an AI agent can reason about and invoke autonomously. This process is not merely a syntactic translation, it is an architectural metamorphosis that bridges the deterministic world of RESTful web services with the probabilistic nature of large language models, LLMs. Now, let's talk about the problem of semantic dissonance. At its core, an AI agent operates on intent and context. When a user requests, check the inventory for the new smartwatch and notify my team if it's below 50 units, the agent must decompose this into actionable steps, query a database, compare a value, and send a message. Traditional REST APIs, however, speak only the language of HTTP verbs, URIs, and structured payloads. They possess no intrinsic understanding of inventory, smartwatch, or notification. This creates a semantic dissonance. The API knows how to perform the operation, e.g., get/API/inventory/ID, but the AI agent knows what the user wants to achieve. Without a bridge, the agent is forced to guess parameter mappings and endpoint structures, leading to brittle, error-prone interactions. Converting an API into a plugin resolves this dissonance by wrapping the procedural HTTP call in a semantic envelope. This envelope provides the LLM with the necessary context, what the function does, what parameters it requires, and how to map natural language concepts to concrete data types. Let's discuss the kitchen analogy, recipes versus raw ingredients. Imagine a master chef, the AI agent, working in a kitchen equipped with a pantry full of raw ingredients, the legacy REST APIs. The pantry contains flour, eggs, sugar, and spices, but they are unlabeled and stored in random containers. To bake a cake, the chef must first identify the correct ingredients, measure them precisely, and combine them using specific techniques. If the chef is an expert, they might succeed. However, if the chef is an apprentice, a less capable model, they will struggle. They might grab salt instead of sugar, or use an egg without cracking it. Plugins are the pre-measured, labeled recipe cards. Inputs: 2 cups flour, 3 eggs, 1 cup sugar, the parameters. 2. Process: mix dry, beat wet, combine, bake at 350 degrees Fahrenheit, the execution logic. 3. Output: a cake, the result. In the context of semantic kernel, the plugin transforms the raw API endpoint into a recipe the AI can follow without needing to understand the underlying chemistry, HTTP protocols, or pantry layout, server URLs. The AI simply reads the recipe, the plugin definition, and executes the steps. Let's discuss the kernel plugin architecture, a unified interface. In semantic kernel, the kernel plugin class serves as the container for these capabilities. It abstracts away the implementation details, presenting a uniform interface to the AI kernel. Whether a function is a local C# method, a prompt template, or a remote HTTP call, the agent interacts with it through the same kernel function abstraction. This is critical because it allows the planner, a component discussed in previous chapters, to treat all capabilities as interchangeable nodes in a graph. The planner doesn't need to know if getWeather is a local calculation or a call to api.weather.com. It only needs to know that invoking getWeather with a location parameter returns a forecast. Turning our attention to the REST API operation runner, dynamic HTTP execution. The theoretical engine driving the conversion of REST APIs is the REST API operation runner. Unlike traditional SDK generation, which produces static, hard-coded client classes, the REST API operation approach is dynamic and metadata-driven. Operation ID, the unique identifier for the endpoint. Path and method, the URI template and HTTP verb, get, post, etc. Parameters: inputs, query, path, header, body, with types and constraints. Responses: expected status codes and return schemas. The REST API operation runner uses this metadata at runtime to construct and execute HTTP requests. This is a shift from compile time binding to runtime orchestration. Adaptability: if the API changes, e.g., a new optional parameter is added, we only update the metadata definition. The underlying runner logic remains unchanged. This allows the AI to adapt to API drift without requiring a full recompilation of the agent. 2. Context window efficiency: instead of feeding the LLM the raw OpenAPI JSON, which can be massive, we can semantically summarize the operation. The runner handles the translation from the summary back to the precise HTTP call. 3. Complex parameter mapping. AI models often output arguments in natural language, e.g., next Monday. The runner is responsible for the coercion and mapping phase, converting next Monday into the ISO 8601 format required by the API, October 30, 2023 T0 second C. Now, let's talk about authentication and security, the gatekeeper pattern. A theoretical challenge in exposing APIs to AI is security. An AI agent should not manage raw API keys or OAuth tokens directly, doing so exposes sensitive credentials to the model's context window and potential leakage via logs or prompt injection attacks. Parameter extraction. The agent identifies the required auth parameters, e.g., authorization, bearer token. 2. Credential injection. Instead of the AI providing the token, a secure HTTP handler injects it. The AI only needs to know that authentication is required, not the secret itself. 3. Policy enforcement. Handlers can enforce rate limiting, retry policies, and circuit breaking, ensuring the AI agent doesn't overwhelm the legacy system. This separation of concerns ensures that the semantic layer, what the AI knows, is decoupled from the security layer, how the system is protected. Now, let's explore semantic wrappers, from intent to structured call. The final theoretical pillar is the creation of semantic wrappers. While the REST API operation runner handles the mechanics of the HTTP call, the semantic wrapper handles the translation of intent. A raw API call is brittle. If an AI tries to construct a JSON body based on a user's vague request, it might omit required fields or use incorrect data types. A semantic wrapper acts as a strict contract. Consider a legacy API endpoint post/orders. It requires a complex JSON body. This JSON snippet defines a data structure, likely representing an order or a shopping cart. Notice how we use nested objects to group related information. For instance, customer details are encapsulated within their own object, as are shipping details. This architectural choice promotes modularity and readability, making it easier to understand the data's purpose at a glance. If we were to flatten this structure, retrieving customer-specific information would require parsing through a much larger, less organized object, increasing complexity and potential for errors. This hierarchical approach aligns with best practices for structuring complex data, especially in API responses or database schemas, where clarity and maintainability are paramount. It also makes it straightforward to validate specific sections of the data independently. If we expose this raw structure to the LLM, it might hallucinate fields or misformat the shipping object. By creating a semantic wrapper, we define a prompt template that guides the LLM to extract only the necessary information. The wrapper acts as a filter and a constructor. User input: order 5 units of the X1 laptop to my office. 2. Semantic wrapper: plugin receives the natural language. 3. LLM invocation: internal the wrapper uses a prompt like, given the user request, extract the SKU, quantity, and shipping address. Output valid JSON matching the schema defined in order_schema.json. 4. Structured output: the LLM outputs a clean, validated JSON object. 5. Execution: the REST API operation runner takes this structured JSON and executes the HTTP post. This pattern enforces reliability. The AI is not guessing the API structure, it is filling in a form defined by the plugin. Now, let's talk about visualizing the architecture. The following diagram illustrates the flow from the user's natural language request, through the plugin abstraction, down to the HTTP execution, and back. This diagram illustrates how the AI translates a user's natural language request into a structured API call via a plugin abstraction layer, executes the HTTP request, and returns the response to the user. Turning our attention to theoretical foundations. Records and immutability: the metadata describing an API operation, parameters, paths, is effectively immutable data. Using record types ensures that once an operation is parsed from an OpenAPI spec, it cannot be accidentally modified during execution, providing thread safety for concurrent agent invocations. 2. Pattern matching: when the REST API operation runner processes parameters, it uses pattern matching to determine how to serialize data. Is this parameter a query string? A path segment? A JSON body? Pattern matching allows the runner to switch strategies cleanly based on the parameter's metadata type. 3. Source generators: theoretical extension. While the runtime approach is dynamic, source generators could theoretically be used to precompile OpenAPI specifications into highly optimized kernel plugin classes during build time, reducing startup latency for agents requiring strict performance guarantees. 4. Async/await streams: API calls are inherently I/O bound. The theoretical model relies on async enumerability to stream responses back to the agent, allowing for progressive processing of large datasets without blocking the agent's reasoning cycle. Converting APIs to plugins is the act of semantic translation. It bridges the gap between the rigid, structured world of HTTP and the fluid, intent-driven world of AI. By utilizing a metadata-driven runner, REST API operation, and semantic wrappers, we create a system where the AI doesn't just call an API, it understands the capability the API provides, maps its intent to the required inputs, and executes the call securely and reliably. This transforms the AI from a passive text generator into an active participant in the digital ecosystem. Let's discuss basic code example. Imagine you have a legacy weather forecasting service, a REST API that your company has used for years. It provides a simple endpoint like get/forecast, city equals London and days equals 3. You want to build an AI agent that can answer user queries like, what's the weather like in Paris for the next 5 days? Instead of hard-coding a specific function call, you want the AI to understand the user's intent, map it to your existing API, and execute it dynamically. This is the core problem we solve, converting a standard REST API into a plugin that the AI agent can discover and use. Let's discuss basic code example, the Weather API plugin. This example demonstrates how to take a simple OpenAPI specification for a weather service and convert it into a semantic kernel plugin. We will simulate the API call using a mock HTTP client for a fully self-contained demonstration. At the beginning, we import necessary namespaces. Notice Microsoft.SemanticKernel, line 1, which provides the core functionalities for building AI agents, and Microsoft.SemanticKernel, plugins.OpenAPI, line 2, which is crucial for integrating external APIs defined by OpenAPI specifications. We also include system, text, JSON, line 3, and system, text, JSON, serialization, line 4, for handling JSON serialization and deserialization, particularly for mapping our C# objects to and from the JSON structures expected by our mock API and the OpenAPI definition. These imports are the foundation for connecting our C# application to the AI orchestration capabilities of semantic kernel and external services. Here, from lines 6 to 13, we define a C# record named weather forecast. This record serves as a data transfer object, DTO, that strongly types the structure of the weather forecast data we expect to receive from our API. Notice the property, JSON property name, attributes. These are vital for system, text, JSON to correctly map JSON property names, which often use snake_case or kebab case in APIs, to our C# property names, which typically use Pascal case. Without these attributes, the JSON deserializer wouldn't know how to match temperature_Celsius from the API to temperature Celsius in our C# record, leading to deserialization failures or null values. This explicit mapping ensures data integrity and readability in our C# code. From lines 15 to 29, we begin defining the OpenAPI spec constant. This multi-line string contains a simplified OpenAPI 3.0.1 specification. In a real-world application, this specification would typically be hosted as a JSON file at a URL, but for this self-contained example, embedding it directly as a string makes the code runnable without external dependencies. Notice the OpenAPI version, line 20, info block, lines 21 to 23, and especially the servers array, lines 25 to 29. The servers array specifies the base URL for the API. This is critical because semantic kernel uses this URL to construct the full endpoint for API calls. If this were incorrect, the kernel would attempt to call the wrong URL, resulting in network errors. This section sets the stage for how semantic kernel will understand and interact with our simulated weather service. Continuing with the OpenAPI spec, lines 30 to 43, we define the /forecast path and its get operation. This is where we describe the specific API endpoint that retrieves weather forecasts. The summary, line 33, provides a human-readable description, and operation ID, line 34, is crucial. Semantic kernel often uses the operation ID to generate the function name within the plugin. So, getForecast here will likely become a function like weatherplugin.getForecast in our kernel. The parameters array, lines 35 to 43, defines the inputs for this API call. Notice the city parameter, lines 36 to 43, within, query and required, true. This tells semantic kernel that city is a mandatory query parameter, which it will extract from the user's prompt or direct function arguments and append to the URL. This detailed specification is what allows the AI to understand how to use the API. Still within the OpenAPI spec, lines 44 to 51, we define the days parameter for our /forecast endpoint. Similar to city, it's an in, query, parameter, but it's required, false and has a default, 1. This means if the user or the AI doesn't explicitly provide a value 4 days, the API will default to returning a forecast for 1 day. This flexibility is important for user experience and robustness. Semantic kernel will parse this and understand that days is an optional integer parameter. This level of detail in the OpenAPI spec is what empowers semantic kernel to automatically construct HTTP requests from high-level prompts or function calls, abstracting away the complexities of RESTful API interactions. Moving to the responses section of our OpenAPI spec, lines 52 to 68, we describe what the API returns upon a successful 200 HTTP status. This content block, lines 57 to 68, specifies that the response will be application/JSON and, importantly, defines its schema. Notice the type, array, and items, $f, #components/schemas/weather forecast. This tells semantic kernel, and any other client, that the API returns a list of weather forecast objects. The $f is a powerful OpenAPI feature for reusing schema definitions, preventing duplication and ensuring consistency. Without this detailed response schema, semantic kernel wouldn't know how to interpret the JSON payload, making it difficult for the AI to understand the data it receives back from the API. Finally, completing our OpenAPI spec, lines 69 to 85, we define the components.schemas block. This is where reusable data models are declared, and here we define the weather forecast schema. Observe how the properties city, date, temperature_Celsius, and description are defined with their respective types. Critically, the date property is specified as type, string, format, date. This hint helps semantic kernel, and other tools, understand that while it's a string in JSON, it represents a date. This schema directly corresponds to our C# weather forecast record defined earlier, lines 8 to 13. The consistency between the OpenAPI schema and our C# DTO is paramount for seamless data binding and for the AI to correctly interpret the structured information it receives from the plugin. From lines 88 to 96, we introduce mockweather HTTP client, a custom class that inherits from HTTP client. This is a crucial architectural decision for this example, enabling it to run without an actual external weather API. By overriding the sendAsync method, line 91, we intercept all HTTP requests that would normally go over the network. Notice the await task, delay, 100, cancellation token, on line 95. This simulates network latency, which is a good practice even in mocks, as it helps identify potential race conditions or UI blocking issues that might arise from synchronous operations in a real-world scenario. This mock client allows us to control the API's behavior and test our semantic kernel integration in an isolated and predictable environment. Continuing within our mockweather HTTP client, lines 97 to 104, we check if the incoming request's URI contains /forecast. This ensures our mock only responds to the expected endpoint. If it matches, we then parse the query string parameters using system, web.httputility.parseQueryString, line 101. This step is essential because semantic kernel, when invoking the plugin, will construct an HTTP request with parameters like city and days as query parameters, exactly as defined in our OpenAPI spec. Our mock needs to correctly extract these to simulate a dynamic response. For instance, var city equals query, city. Unknown, line 102, demonstrates how we safely retrieve the city parameter, providing a fallback if it's missing. This ensures our mock accurately mimics the behavior of a real API. Still in the mockweather HTTP client, lines 105 to 114, we proceed to generate mock forecast data. This enumerable, range and select LNQ query, lines 106 to 114, creates a list of weather forecast objects. Notice how it uses the city and days parameters extracted from the request to generate relevant data. For example, date_only.from datetime, now.addDays, line 109, simulates forecasts for future days, and random, shared.nextDouble, *10, line 110, adds variability to the temperature. This dynamic data generation makes the mock more realistic and allows us to test different scenarios, e.g., forecasts for various cities and day ranges. Without this, our mock would return static data, limiting its usefulness for testing the AI's ability to handle diverse API responses. Concluding the mockweather HTTP client, sendAsync method, lines 115 to 123, after generating the mock forecasts, we serialize them into a JSON string using JSON serializer, serialize, forecasts, line 115. This is crucial because real APIs return JSON. Then, we construct an HTTP response message with an OK status, line 116, and embed the JSON string as its content, lines 117 to 119. Note the system, text, encoding.utf8 and application/JSON content type. These headers are vital for the client, in this case, Semantic Kernel's OpenAPI plugin, to correctly interpret the response body. If we didn't specify application/JSON, Semantic Kernel might not know how to parse the content, leading to errors. This entire process ensures that our mock behaves exactly like a real JSON API from the perspective of Semantic Kernel. Moving to the program class and main method, lines 126 to 139, we begin the core Semantic Kernel setup. At line 133, kernel.createBuilder initializes a kernel builder. This builder is a central component for configuring our AI application, acting as a dependency injection container for Semantic Kernel. Notice builder, services.add singleton HTTP client, new mock weather HTTP client, on line 136. This is a critical step. We are registering our custom mock weather HTTP client as the HTTP client instance that Semantic Kernel will use. This means any subsequent calls within Semantic Kernel that require an HTTP client will receive our mock, ensuring our plugin interacts with the simulated API. Finally, bar kernel equals builder, build, line 139, constructs the immutable kernel instance, ready to orchestrate AI tasks and plugins. From lines 141 to 159, we proceed with plugin creation from our OpenAPI specification. First, we convert our OpenAPI spec string into a memory stream, lines 143 to 144. This is necessary because import plugin from OpenAPI async expects a stream. The core action happens on lines 147 to 159, await kernel.import plugin from OpenAPI async. This method is a cornerstone of Semantic Kernel's integration capabilities. It parses the OpenAPI specification, automatically discovers the API's operations, like getForecast, and generates callable functions within the kernel. The OpenAPI function execution parameters, lines 151 to 159, are highly important. We explicitly pass our HTTP client, line 154, to ensure the plugin uses our mock. Enable dynamic payload equals true, line 156, allows Semantic Kernel to automatically map prompt inputs to API parameters, a powerful feature for AI-driven interactions. Enable functions equals true, line 158, ensures the AI can discover and use these functions. Without these parameters, the plugin might not function as expected or might try to use a default HTTP client. After successfully loading the plugin, lines 161 to 171 provide console feedback, confirming the plugin's availability and listing its functions. This is helpful for debugging and understanding what the kernel has learned from the OpenAPI spec. Then, we prepare for AI invocation. var prompt equals, what's the weather forecast for London for the next 3 days, line 167, defines the user's natural language query. The magic here is that this is a semantic prompt. The AI is expected to understand the intent and map it to the appropriate tool. We are not explicitly telling the AI to call getForecast, instead, we're asking a question that getForecast is designed to answer. This demonstrates the power of Semantic Kernel's orchestration. The AI reasons about which tools to use. On lines 172 to 178, we execute the prompt using await kernel.invoke prompt async, prompt. This is where Semantic Kernel's AI orchestration comes into play. When this method is called, the kernel, in conjunction with the underlying large language model, LLM, which would be configured elsewhere, not shown in this snippet but typically via builder.add OpenAI chat completion or similar, performs several steps. 1. Intent recognition *. The LLM analyzes the prompt to understand the user's goal. 2. Tool selection *. It identifies that the weather plugin.getForecast function is relevant to answer the query. 3. Parameter extraction *. It extracts the necessary parameters, city, London, days, 3, from the prompt based on the OpenAPI schema it was given. 4. Function invocation *. It then calls the getForecast function, which in turn uses our mock weather HTTP client to simulate the API call. 5. Response interpretation *. The LLM receives the mock API's JSON response, interprets it, and formats it into a human-readable answer. This entire process showcases how Semantic Kernel bridges natural language understanding with external tool execution. Finally, from lines 180 to 194, we demonstrate an alternative, more direct way to invoke a plugin function, bypassing the AI's natural language reasoning. This is useful when you, as the developer, already know exactly which function to call and with what arguments. We retrieve the specific function using weather plugin, getForecast, line 184. Then, we create kernel arguments, lines 185 to 188, to explicitly pass the city and days parameters. Await kernel.invoke async function, arguments, line 190, then directly executes this function. This approach is powerful for scenarios where you need programmatic control over tool execution, such as in automated workflows or when building specific features that don't require the AI's interpretive layer. It highlights the flexibility of semantic kernel, allowing both AI-driven and explicit function calls. To resolve parameter extraction issues, the flow can be visualized either by using semantic prompts to guide the AI or by employing the direct invocation pattern where the code handles extraction and validation before calling the plugin. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. Thank you for your attention. This lesson is excerpted from Volume 8, Chapter 7 of the C# and AI Masterclass ebook series and from the volume, The Core of AI Engineering, Microsoft Semantic Kernel and Agentic Patterns. You can find all the details here, https://github.com/edgarmilvus/C# programming series. The ebook also includes 20 chapters with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.